Okay, so the question was when we will start having these take-home assignments, exams. Made a mistake. I made the mistake of giving 2 take-home assignments in summer 1 because it was the first time I'm teaching in summer. I didn't realize how fast time goes by. So I was thinking of splitting it into 3 or 4 parts for this term, and actually giving one sometime this week, which is like the first half of the first exam I gave last term. So let me check the calendar here. I didn't make a tentative plan yet, but it would be probably like so we have, I could give one on July 12 or 13 by the end of this week. So let's say the first one could be July, so I'm going to assume 13. Let's say I give these on a Friday, and then I give you 10 days, so it's going to be 23rd. So this could be due 23rd. We could do a second one immediately after. So we could do one on 27. I don't think we can fit 4 of these if I give 10 days each. I like giving 10 days for take-homes. So 27 to maybe August 6. So this could be up to August 6, and the third one could be around August 10. So 2 then around August 20, which is the last week of classes, and then your projects are due, let's say, by August 23. Right. So let's say these are take-home 1, take-home 2, take-home 3, and projects. Yes?
How is the format of the test going to be?
How is the format? It's going to involve doing some math and writing some code. So it's like a homework, basically. Yes?
We do like maybe an example or 2 every now and then. The problems that we
We'll start doing examples in class. And the reason I give these extended durations is so that it's like a homework, and in between we can discuss. You can contact me at office time, or in class we can discuss the questions. So my goal is to make sure that everybody is able to solve all of these problems successfully, right? So time basically is not a limitation. So everybody, I think if you start working on these assignments on the day I give them, use the first weekend to make an attempt, come back with questions for the next week, use the class time and office time to clarify your mind on those questions, use the following next weekend to finish off. I think everybody should be able to get these done. Yes? You can each chapter has a bunch of problems. I selected some problems. I mean, there's no end to the number of practice problems you can solve, so I could bombard you with practice problems. But the questions will not necessarily be like those in the book. So you'll see this week. They're not hard, I think, but because you're doing this for the first time, it will appear hard to you perhaps when you're making your first attempt. But make sure to use this time in between to talk to me, and we'll get you on on the right track, and you'll do all of these. Yes.
So these take-home tests, will they cover the material up to that date, or will it include material that we're learning in between those two dates?
Yes. So they will not overlap for the most part. So they will be their intersection will be approximately empty, let's say. So the first one will be on Bayesian decision making, an estimation that we will talk about those soon. The last one, let me try to remember the questions. So at the end, we'll be talking about support vector machines towards the end. So definitely you'll implement a support vector machine here for the last one. Basically, I'll make you implement all the critical things and produce results. Right, so don't think of these as exams, think of them as homeworks. Right? Okay, so this is probably a good plan. That way, yeah, we can have basically one every, I guess, 2 weeks or so, right? And then 3 of those followed by a project. So I'll try to split the 2 exams I had from before to 3 exams. I'll probably modify a little based on lessons learned from previous exams. So what I want to start doing today is derive principal component analysis and linear discriminant analysis, right? So that we can get started on machine learning, and then I can ask about those here. Ask you to implement them. Let me put my computer to sleep for a while. So, it's a limited battery. Okay. Did anybody use principal component analysis before, by any chance, for anything? No? Did you hear about it? Yes? Okay, so this is a very basic dimension reduction method. So we'll call it PCA. The goal is the following. Let's say I have n-dimensional random vector x, okay, that takes real values. So let's assume the expected value of x is 0 and covariance of x is matrix sigma. So this is a real vector, of course, and this is a positive semi-definite real matrix. So remember, covariance is equal to expected value of, let's call this mu of x. Let's call this mu, not mu of x. So covariance is x minus mu, x minus 2 mu transpose expected value of this quadratic term, right? And when mu is equal to 0, according to this assumption, covariance becomes expected value of xx transpose. Okay, so we'll make use of this. Let me take this away. Okay. So I'm interested in finding a linear linear projection of x. Okay, so find a linear projection. Right, so we'll call that y equals w transpose x. So I need to find a vector w such that when I project x onto this vector, the resulting random variable y, right? So w is my parameter vector, that's n-dimensional. Y is a real valued scalar random variable. I'm interested in making the variance of this variable maximum. Okay, So clearly expected value of y is 0. Right, so expected value of y is expected value of W transpose X. But expectation and inner product with a vector are both linear, so I can swap the order. So this is W transpose expected value of X, and expected value of X is 0. Right, so this is 0, so this is 0. So expected value of y is 0, which means variance of y is equal to expected value of y squared. Right? Normally, expected variance is y minus mean of y squared, but since the mean value of y is 0, variance is now expected value of y squared. So similar to here. So since mean of x is 0, mean of y is 0, and variance becomes equal to second order moment. Yes.
Why do we want to maximize variance?
Yeah. So I want to find a projection that maximizes the variance. Okay. So I'll show you later why. Okay. So maximize the variance of y by finding an optimal W. But if you look at variance of y, right, so variance of y is, since it's 0 mean, it's expected value of y squared, which is expected value of W transpose X squared, right? So if I write this explicitly, W transpose X, I'm going to multiply it with W transpose X again, but I'll flip the order. Right, so this is y squared. Again, I'll take these W's outside the expectation. So this is W transpose expected value of X, X transpose W. And expected value of X, X transpose is sigma, the covariance matrix. So variance of y is, in this case, W transpose sigma W. Okay, so I'm interested in maximizing this. Right, so maximize W transpose, sigma W. Okay, but I can make this quantity larger simply by making the length of W larger. I'm interested in finding a direction such that when I project my data X along to a line along that direction, the variance, the spread is large, and I don't want the spread to become large just by making the length of the projection vector large. So we'll maximize this subject to a length constraint. Right, so subject to length of W equals 1. Okay, so I don't want the length of W to impact my variance. I want its orientation to control the variance. So if I have a Gaussian, just for illustration, why do I want to maximize variance? So let's look at an example, and we'll do a numerical example later. So suppose my X comes from a Gaussian for illustration purposes. It's, let's say, two-dimensional. So I have a 0 mean and some covariance. So if I draw the one equilevel contour of this Gaussian PDF, so here's my first component, second component. This Gaussian PDF is centered around the origin because the mean is 0, right? And depending on the eigenvectors and eigenvalues of sigma, the equilevel contours will be ellipses that are tilted and elongated. So I'll have equilevel contours that look like this. Perhaps, right? So in this case, the eigenvectors of sigma are these. So the eigenvectors, sorry, my drawing isn't perfect, but the major axes of these ellipses will be aligned with one eigenvector, and the minor axes will be aligned with the other eigenvector. Okay. So these there will be two eigenvectors of the sigma, and eigenvalues will determine the elongation of the axis. Okay. So I'm interested in projecting samples from X to a direction on which variance is maximum. Unfortunately, this classroom gives me only black and white, so I'll try to illustrate here. So let's say I projected my data along this line. So let's say W is along this direction. So if I project a two-dimensional Gaussian along this line with length 1 W, since the length of W is 1, that's not going to stretch anything. It's just going to be this Gaussian projected. So I'll get a one-dimensional Gaussian that has a 0 mean. Okay. So I'll get a one-dimensional Gaussian PDF along this, and the spread, the sigma corresponding to this choice of W will be whatever. So I can rotate W in this two-dimensional case. I can rotate W to see all possible cases. So one choice is choose W to coincide with the minor axes of these ellipses. So my Gaussian will be in that case the narrowest in 1D case. I can rotate the vector towards the main axis, and then I'll get a wide Gaussian. So my Gaussians will become from narrow to wide, and then as I keep rotating, they will become narrower again. So the variance of the projected random variable will go down. I'm interested in finding this direction along which I capture most of the variability in the data. So this is how people started doing PCA. I have multidimensional data. Can I find a vector such that along that direction the spread of the data is maximum? And I'm going to measure spread by variance, which means I'm going to look for this vector that maximizes variance to find that direction. So you could also look for a minimum variance direction. Then it would be some other direction. So, yes.
So the point of ECA is to be able to look at high-dimensional data in smaller dimensions.
Yes. So that's why I called it's a dimension reduction method. So my goal is to reduce the dimensionality of data while maintaining variance maximally. Right. So I want to find a lower dimensional representation, approximation of the data, which has maximum variance. So I want to capture the spread of the data in a lower dimensional space as much as possible. And my quantification of capturing that spread in lower dimensional space is variance. So there are dimension reduction methods that use other objectives. And this is just one of them, the oldest. Okay, so I'm interested in maximizing this subject to W transpose W minus 1 equals 0. Right? So I'll just write my equality constraint in standard form. So we'll prepare the Lagrangian. Remember, at the optimal solution of a constrained optimization problem, the derivative of the Lagrangian with respect to the parameters will become 0. So let's write the Lagrangian. So Lagrangian is my objective minus lambda. Lambda is the Lagrange multiplier for this constraint. Okay, so that's the Lagrangian. We'll take the derivative of the Lagrangian with respect to the parameters, which is W, and write it as a column vector. Okay, so derivative of the Lagrangian with respect to W. I'm writing transpose here so that it becomes a column vector. Okay, so the derivative of a quadratic term with a symmetric matrix in the middle is 2 sigma w. You can go check the matrix cookbook for this. So 2 sigma w, that's the derivative of the first term. Second term minus 2 lambda w, right? So at my solution, this should become 0. So I'm going to solve for this. Remember the KKT conditions. The second and third conditions in the general case said your equality and inequality constraints must be satisfied. So those are actually recovered by also taking the derivative of the Lagrangian with respect to lambda. So I need to satisfy my equality constraints, which is this is equal to 0. Sorry, so this is equal to 1. If I multiply, well, let's divide this by 2. So if I multiply the first equation with W transpose from left, right, so I have W transpose sigma W must be equal to lambda W transpose W. That's the first equation multiplied from left with W transpose, and then just rearranging things. But W transpose W must be 1, right? So that means lambda must be at the solution. Lambda must be W transpose sigma W. Again, looking at the solution here, I must have sigma W equals lambda W, right? So if I combine these two pieces of information, I need my W will be, the optimal W will be an eigenvector of sigma, right? So W is an eigenvector of sigma. And the corresponding eigenvalue lambda, right, which is equal to W transpose sigma W, that's the objective that I was trying to maximize, right? So I have a choice of eigenvectors here. There are n different eigenvectors. I must choose the one that has the largest eigenvalue, right? So W then is the eigenvector of sigma with the largest eigenvalue. Okay, so the solution to this problem is the eigenvector with the largest eigenvalue. Okay, so I'll say, let's say sigma can be decomposed into its eigenvectors and eigenvalues like this, where Q is orthogonal, lambda is diagonal, right? And suppose this lambda has eigenvalues sorted such that lambda 1 is largest, lambda 2 is the second largest, and so on. So we order the eigenvalues from large to small, sort the eigenvectors accordingly, so that Q becomes, in the first column of Q, I have the eigenvector for the largest eigenvalue. Second column of Q is the eigenvector for the second eigenvalue, and so on. Right. So W must be then Q1, right? So W equals Q1, the eigenvector with the largest eigenvalue. Okay, let's write this down here. So I'm going to call this Y1. This is the first projection, right? So I can do more projections, and I will do it. So we call this projection of X onto the first eigenvector, right, corresponding to the largest eigenvalue. And notice that here eigenvectors are normalized. Right, so they're unit length and they're orthogonal. So this is a unit length eigenvector which satisfies my constraint. Okay. So we call this projected random variable Y1 the first principal component. Okay. So first principal component of X. So since there's a first principal component, then you probably then realize people asked, can I find the second one with some additional properties? So let's try to then find the second projection that also has maximum variance. So I'll write it as W transpose sigma W. And again, my projection vector must be unit length. I'm interested in making the second projection uncorrelated with the first one. So I want expected value of so this will give me a second projection y. I already committed to a first projection y1, and I want these to be uncorrelated. Remember, when two random variables are uncorrelated, their expected value of their product is equal to product of their expected values, but these are zero mean. So basically I want them to be orthogonal. So starting with orthogonal uncorrelatedness constraint, using the fact that they will be zero mean, this becomes an orthogonality constraint. So what is expected value of y1? This is expected value of W transpose X, and y1 is Q1 transpose X or X transpose Q1. So this needs to be 0, but this is equal to W transpose expected value of X transpose is sigma Q1, right? I can take these vectors out. So this will be 0. So that's my second constraint. So I want my second projection to be uncorrelated which in the case of zero mean projections means this. So I want this constraint to be satisfied by W. Okay, so let's write the Lagrangian. Now I have two constraints. So, okay, lambda 1, lambda 2. So there will be two Lagrange multipliers. Okay, so we'll have Lagrangian is W transpose sigma W minus lambda 1 W transpose W minus 1 minus lambda 2. This is already in standard form, sigma Q1, right? So that's my Lagrangian. Again, we'll take the derivative with respect to W. So take the derivative. Let's make it in column form. So again, this is 2 sigma W minus 2 lambda 1 W, and the third term is minus lambda 2 sigma Q1, right? So that's the derivative with respect to W. So that should become 0 at the solution. So I have this equation to be satisfied. I also have these constraints to be satisfied. So I have W lambda 1, lambda 2. Those are the unknowns. I have the same number of equations, so I can solve this, right? Let's do the same trick. Multiply with from left with W. Okay, so if I multiply from left with W, we have 2 W transpose sigma, from left with W transpose. So 2 sigma W transpose sigma W minus 2 lambda 1, that's going to be 1. 2 lambda 1 W transpose W will be 1 minus lambda 2 W transpose sigma Q1. The second constraint says this should be 0, and that should be 0, right? So that again tells me lambda 1 should be W transpose sigma W. So this means lambda 1 is W transpose sigma W. So that's an equation to satisfy. Let's also multiply from left with Q1. I think Q1. This is the part I always have to think a little. So let's try Q1 transpose. So if I multiply with Q1 transpose from left, yeah, I think this is good. Minus 2 lambda 1. Oh, I need to do some more work there. That's why it's. Hold on, let's just write this and then simplify. Q1 transpose W minus lambda 2 Q2. Q1 transpose sigma Q1. So this should be 0. Okay, so because sigma is symmetric, this constraint says this first term should be 0. Okay, so I don't know what to do with this second term here yet, but let's work on this constraint here a little. I think okay, so since Q1 is an eigenvector of sigma, sigma Q1 is lambda 1 Q1. If I plug that in here, this is equal to lambda 1 W transpose Q1 equals 0. And lambda 1 is not equal to 0, so that must mean an equivalent condition is W transpose Q1 is 0. So this constraint also means W transpose Q1 equals 0 because Q1 is an eigenvector of sigma. So these are equivalent conditions. Yes. So we started with the desire to make the second projection uncorrelated with the first one. But we assume X is 0 mean, so that makes Y and Y1 0 mean. So these being uncorrelated means expected value of Y, Y1 should be 0. Then I start substituting for Y, W transpose X, for Y1, Q1 transpose X. Right? So that's plugging in the values. And then taking the constant vectors out of the expectation so that it's W transpose sigma Q1. Right? So this quantity, which must be 0, is this expression. So this became our constraint, which we used. But because Q1 is an eigenvector of sigma, actually sigma Q1 is lambda 1 Q1. Q1 is the eigenvector corresponding to eigenvalue lambda 1. So here I can substitute lambda 1 Q1. So it's W transpose lambda 1 Q1 equal to 0, which is this. So these two are equivalent forms of the same constraint. So this constraint says both this should be 0 and this should be 0, W transpose Q1. So here we have W transpose Q1. So this constraint makes, when I satisfy this constraint, both of these are 0. And from here, since Q1 transpose sigma Q1 is lambda, let me make these gamma. I didn't realize. So my Lagrange multipliers and eigenvalues are getting mixed. So these are gamma. Okay. So gammas are Lagrange multipliers, lambdas are eigenvalues of sigma. Okay, so gamma 2, the second Lagrange multiplier, must be 0. Right? Because these are 0 when I satisfy the constraints. Here, Q1 transpose sigma Q1, this is lambda 1, the eigenvalue, largest eigenvalue here, which is hopefully greater than 0. Otherwise, you don't have any variance to maximize. Right? So when this is positive, that means gamma 2 must be 0. Okay, so I have gamma 2 equals 0. gamma 1 equals W transpose sigma W, and I have this equality for W. So since gamma 2 equals 0, I can drop this. Again, we're down to sigma W equals gamma 1 W, right? So then sigma W equals gamma 1 W, and gamma 1 is W transpose sigma W. So same story here. W must be an eigenvector of sigma with the largest possible eigenvalue. Right. So since gamma 1 will be an eigenvalue, but it cannot be lambda 1 because I cannot make W equal to Q1. W must be orthogonal to Q1. So it must be one of the other eigenvectors. The next eigenvector in line is Q2 with the second largest eigenvalue lambda 2. So that means W will be, in this case, the second eigenvector, okay, corresponding to the second largest eigenvalue. So after I solve the second problem, now I have a second projection. So this is called the second principal component of X. Okay. Any questions? Yes.
So why would we want something orthogonal to the direction of the lowest variability? Wouldn't that be the
Uncorrelated. Yeah, we wanted them to be uncorrelated. Remember, for Gaussian random variables, if my X is multivariate Gaussian, then making pairs of projections uncorrelated makes them also independent. So if I had a Gaussian random vector X, then this would also achieve independence. So I'm looking for, in the case of a Gaussian, I'm looking for independent linear projections that produce independent, statistically independent random variables with large variances. Okay. So, but if X is not Gaussian, then this is just making them uncorrelated, which is something people like. I mean, historically, people didn't deal with high order statistics. They just dealt with mean and covariance for the most part. So uncorrelatedness was a good thing to have. Mm-hmm. Yes.
Where did you get the first constraint from?
So that's so length of W equals 1 is there to prevent this variance from going to infinity simply by making length of W go to infinity. Right?
But why did you set it to 1?
2. You can set it to 2. It doesn't matter. Yeah, because so here in the solution, it doesn't even appear that particular value. I mean, if you set it to 2, then you'll choose 2 times Q1, 2 times. So you'll just scale everything by 2. So yeah, so it's just gonna change the length of this vector that we're projecting onto.
And then where did you get the y equals WTX? Like, is that just
That's my linear projection model. So this is what we're doing all the time here. Yep.
So is it always going to be like that, or is it just like now?
So so now we're trying to do linear projections, and that's a linear projection.
Okay.
You can do nonlinear projections. So you could have a nonlinear function of X with parameters W. Right. So we'll talk about some of these later.
And then,
Right now we're doing linear.
from the where did you put derivative
Mm-hmm.
to the bottom? Just multiply that whole equation.
Yeah.
with WT.
Exactly. So take the Lagrangian's gradient with respect to W. That's one equation. And I want to make use of these constraints that need to be satisfied. So multiply this with W transpose from left. So it's W transpose multiplying the first equation. And this one is Q1 transpose multiplying the first equation. So, and then,
How did you know to multiply? How did you come up with that?
well, yeah, I just want to get expressions that look like the constraints. I see here a sigma Q1, which looks awfully close to this one. It looks like if I multiply this from left with W transpose, so you just recognize forms. Yeah, yeah, exactly. You try to recreate. You try to end up with expressions that look like your constraints, so that you can then plug in values. get rid of variables. And this is just standard algebra there. So, okay, so let me summarize here what we did. So we're looking for linear projections of this type, W transpose X. Remember, X is zero mean, and expected value of X transpose is sigma. So the first one simply maximized the variance of Y, right? Subject to length of this projection vector being 1. The second one maximized the variance subject to same length condition, and also expected value of Y, Y1 equals expected value of Y, expected value of Y1, which ended up being 0 because of the assumptions there. But so this is a uncorrelatedness, right? So I'm looking for a sequence of uncorrelated linear projections that maximize variance. So I can design a third problem. Right? So maximize variance of Y subject to using a unit length vector. Make this uncorrelated. Let me with Y1 and uncorrelated with Y2. Right? So make the third projection uncorrelated with both of these previous principal components. When you solve this, again, you have now 3 Lagrange multipliers. You do something similar. It just gets more complicated, but you exactly do the same tricks. Multiply with W transpose, multiply with Q1 transpose, Q2 transpose, eliminate stuff. Anyway, so you end up with the third eigenvector. Okay, so if you keep doing this, adding these uncorrelatedness constraints, solving, you get Qn transpose X as your last principal component, right? So we have a sequence of principal components, Y1 to Yn. They are ordered by their variance from large to small. Right, so I can write this in one shot as I'm going to use this matrix Q transpose, which has all these in the rows. Right, so Y is equal to Q transpose X. Right. Right, so if I take X, if I take samples from X, estimate its covariance, estimate the mean, subtract the mean from the samples, right? So that the samples are zero mean. Do eigendecomposition on the covariance. Eigenvector matrix transposed becomes your principal component analysis solution. Right? So I can get all the principal components. The key here is to make sure that when you do eigendecomposition, you sort the eigenvalues and the corresponding eigenvectors in this decreasing order by eigenvalue. Okay. Right, so eigendecomposition methods can give you eigenvalues in a shuffled fashion, so you just need to sort them from large to small and sort the eigenvectors in the same order. Okay, and then you can use Q transpose X or a part of Q transpose. Maybe you want just 3 dimensions. Right, so you'll just keep the first 3 rows. So how do you decide how many of these to keep? Right, because my goal was to do dimension reduction, right? Let's look at the variance captured. So variance of Y1, let's look at variance of Yi, one of these, is equal to since these are all zero mean, this is equal to Qi transpose X squared So I can write it like this, right? So you know this from the previous exercise. So okay. So this is the variance of the ith projection, ith principal component, but this is equal to lambda I qi. So this is lambda I qi transpose qi, but qi's are normalized to unit length. So this is equal to lambda I, right? So the variance of each principal component is equal to the eigenvalue corresponding to the eigenvector we used to project it, right? So produce it. So if I keep the first m principal components, right? So let's say you keep y1 to ym, where m is less than n. You can go up to n. So this is equal to q1 transpose to qm transpose x, right? So I'm going from an n-dimensional data to m-dimensional data, which might be lower dimensional. So the total variance I keep, this is what people call, so if you add the variances of these, because they are uncorrelated, that's somehow a sensible operation. So variance kept over total variance in X is the sum of eigenvalues that you keep over sum of all the eigenvalues in sigma. Right? So this is a quantity that's between 0 and 1. So people like it as a normalized measure of what fraction of the total variance has been retained in your lower dimensional approximation. You can find this denominator easily by looking at trace of sigma, right? So this is equal to trace of sigma. Right? Sum of eigenvalues of a matrix is the sum of diagonal entries. Okay, so basically, without solving for all the PCs, you can find what the denominator is, and then you solve for the first one, look at what fraction you kept, solve for the second one, see what the fraction is after you add a second dimension, and so on. So people typically start with the aim, for example, in not in machine learning, but in other fields that use statistics. They say I'm gonna retain 95% of the total variance in my dimension reduction solution. So their goal is to make this greater or equal to 0.95, and that makes them happy, right? They feel like they captured a sufficient amount of the total variance. So you'll just keep adding principal components until your fraction hops over this satisfies this inequality. So that might happen in the first one or after the 15th one. Okay, so in general, this is not a good way to do it. So machine learning people will not do this, but you'll see this done all the time in papers. Okay. So people talk about total fraction of total variance retained in the principal components. There is one nice property of PCA. So it's a solution to a different problem. As a side note, let me write it here. So suppose I want to find an m-dimensional linear projection. So I want to find y1 to ym, which is equal to w1 transpose to wm transpose x. Okay, so I want to find a linear projection with m vectors. Again, assume this x is zero mean with a covariance sigma. So let's solve the following. So I'll call this matrix W transpose, so W has m columns, n rows. Okay. So let's optimize a matrix W to minimize the squared error between x and an approximation of x reconstructed from y. Right. So an approximation of x is W transpose X. Right, so I will take X, project to Y, which is low dimensional, and I will then reconstruct an approximation of X using W again in this fashion. Okay. So let's look for the matrix that minimizes expected value of X minus X hat squared. Okay, so this is equal to so I minus W transpose X squared, right? So that's X minus X hat, and then you can write this as expected value of X transpose. If I write this norm squared as vector transpose itself, okay, so expected value of this. So let's minimize the expected value of this. Basically, that's minimum mean squared error approximation. So it turns out so this matrix, which uses the first m eigenvectors in its rows, so that's W transpose. So an optimal solution to this problem is a matrix that basically uses the first m eigenvectors of sigma, covariance of X. So the principal components, when stacked together, basically become also this minimum mean squared error representation. So if you want to think of this as data compression, right, from a high dimensional data set to a low dimensional compressed version from which I can reconstruct approximations of the original data. So this is a compressed, this is basically lossy compression. Right, so because I cannot recover the original data in general unless I keep all the eigenvectors, but I can get really close to the original data in this sense. Okay. So nowadays, for example, I mean, you'll learn about autoencoders with neural networks. They essentially do this. They do this in a nonlinear fashion. Right? So instead of WX, W transpose X, this will be a neural network. You'll have a pseudo inverse of the neural network that's optimized simultaneously with the dimension reduction method. Right? And you'll look for a nonlinear dimension reduction from which you can recover approximations of the data. Okay? So that those are autoencoders or encoder-decoder pairs. Okay, so this property of the principal components also might make you happy if your goal is to find representations that can be used to approximately recreate data in the original space. Okay, any questions so far? Let's see. We have two choices. We can derive LDA and then implement these in MATLAB, or we can implement this in MATLAB. I would like to use the time to derive LDA and then start implementing PCA later, and then you can look at the code on your own time. But if you insist, we can go to the code right now. Okay, so because I think you can, yeah. I write code slowly, so I don't want to use our time me writing code slowly. You can do it much faster probably. Okay, so PCA tries to do dimension reduction with the goal of maintaining variance in the reduced dimensional variables. okay, while trying to generate a sequence of random variables that are uncorrelated with each other. Okay, so that's dimension reduction. This is a classification method. Okay, so we'll talk about classification. That's an R. So I want to call this specifically Fisher's LDA, because the optimization objective that we will use is specifically due to Fisher. Okay, so suppose I have two Gaussians now for illustration purposes. So in general, we'll have two random vectors, x1 and x2. Let's say, so these are two random vectors. They are both n-dimensional. And they have means mu1 and mu2, and let's say covariances sigma 1 and sigma 2. Okay. So if these were Gaussian random vectors, this might look like, okay, let's say these are the two coordinates of x for illustration. So my first Gaussian might look like this, with a mean at mu1 and the covariance sigma 1 that determines the shape of these ellipsoid cross contours, equilibrial contours. The second Gaussian might look like this, with a mean vector mu2 and the covariance sigma 2. Right? Let me actually shift it a little to here. Okay. Okay, so I'm interested in finding a vector W such that if I project data coming from this first distribution, first random vector x1, so let's call that the y1. So I'll take a vector from the first set, project onto W, and those will be y1s. And I'll take a vector from the second set, a random vector from the second case, project onto W, and I'll call those projections instances of random variable y2. So I'm interested in finding a W such that these scalar random variables y1 and y2 are as separated as possible from each other. Right, so what does it mean to be separated when the values are random? I need to look at their average separation as well as how spread they are when they're projected. Right. So let's look at, for example, a bad W. Let's say I pick my W to be this vector pointing down right. So the line I'm projecting onto is this. So the first Gaussian projects to about here. So there's a Gaussian about here. It's pretty broad. Okay. The second Gaussian projects to about here. Right, so that's one choice. So there's some overlap here which I don't like. Actually, my drawing is not good, right? So if this projected, it would be right in the middle here. Let me fix so somewhere around here. Okay, so there's huge overlap here that I don't like. I could choose a different W which maybe points this way. Let's call this W prime, the first one. That's a bad one. So if I choose W to go right up, so I'm projecting my two-dimensional x's onto this line. So this first Gaussian will project to about here. So I'll get a Gaussian distribution like this. Second Gaussian will project to about here. and the tails overlap, of course, but the overlap is much better than what I had in the first case. Right, so the first W I chose created a projection direction where the second Gaussian fell right on top of the first one's projection. Right, so a sample in the first set would project to somewhere here. A sample in the second set would project to about the same place. And looking at these y1, y2 values, I wouldn't know where it came from. So my goal is to find a W such that from the projections, I can easily tell which group the data came from. Right? So this is a typical classification problem. So find a scalar value such that when the scalar value is compared to a threshold, like 0, the scalar value greater than 0 says it came from one type, one category, and less than 0 means it came from another category. So we're looking for that kind of a rule that's linear. Okay, so basically I would like to make these projected distributions to be as separated as possible. So I want to maximize the distance between their average values after projection. But I also want to keep these variances of the projections small. Right? Because I can have a very good separation between the means, but if the variances are large, then the overlap is still large. Right? So the relative mean to mean squared to variance ratio is probably a good measure. That's what Fisher thought, and he said, let's say expected value of y1 is m1. So expected value of y1 is m1. So clearly m1 is equal to W transpose mu1. W transpose mu1. Expected value of y2 is, let's call it m2, which is clearly W transpose mu2. Okay. And the variance of y1 is like we had in PCA. It's going to be W transpose sigma 1 W. Variance of y2 is W transpose sigma 2 W. Okay, so let's make the means m1 and m2 separated. Right, so I want to find the W that separates these means from each other. Right, so take the x values, project onto lines such that the average value of the projections are separated maximally in this fashion. But I want to also keep the variances of the projections small. So let's call these sigma 1 squared and sigma 2 squared, small sigmas. So Fisher said, why don't I do this? Okay, maximize that ratio. And this tries to simultaneously accomplish maximum separation between the means of the projections and trying to keep the variances of the projections small, right? Because smaller sigmas will make this ratio larger. Okay, so let's plug in these expressions for m's and sigmas. So this is W transpose mu1, W transpose mu2 squared, W transpose capital sigma 1, capital sigma 2. Okay, so this is Fisher's problem to find a linear projection that separates two distributions with means mu1 and mu2, covariances sigma 1 and sigma 2. So before we proceed, I want to make sure that everybody agrees with Fisher that this is a reasonably good idea. Okay, is that okay? Any questions about this choice? What it means? No? Okay, so I assume everybody is comfortable. So if you like the objective, then it's right. This is our goal. So let's solve. So I'm going to write the numerator a little differently by taking W transpose out from left. So that square can be written as this scalar squared, right? And I'll take this scalar, flip it, and write next to it to square. So this is now squared. Okay, that's the numerator. And in the denominator, we can take W transpose and W out from left and right. So we'll have W transpose, sigma 1, sigma 2, W. Okay, so that's my objective. So here I don't have any constraints on W because both numerator and denominator are quadratic in W. So if I scale W by 5, for example, they both get scaled by 5 squared. So those scale factors cancel each other out. So I don't need to worry about length of W contaminating my choice, basically. Okay, so let's give these matrices names, as is typically the case. So the numerator matrix is typically called the between scatter matrix. So that's mu1 minus mu2, mu1 minus mu2 transpose. So that's a rank 1 matrix, right? Which means one eigenvalue is mu1 minus mu2 length squared. All the other eigenvalues are zeros. And this thing in the denominator, that's within class scatter matrix. So this is between class and this is within class scatter matrix. So they capture how the classes are separated and how much each class is spread within itself. Okay, so that means I'm going to maximize W transpose S between, W transpose S within. Okay. So let's take the derivative equate to 0. So this is an unconstrained problem. So the derivative of let's call this f of W that I'm trying to maximize. Oops. Derivative of this, I'll write it in column form. Okay, so derivative of a ratio is derivative of the numerator, which is these are both symmetric matrices, so it's 2SBW. Derivative of numerator times the denominator, right? Minus derivative of denominator times numerator. Okay, divided by denominator squared. Okay, so this should be equal to 0 at the solution. Let's assume this sigma 1 plus sigma 2 matrix is positive definite, so that the denominator does not become 0. In that case, at the solution, the numerator must become 0, so I can divide by 2 and move this second term over to the right side. So at the solution, I must have, let me also divide by this quantity. So I must have okay. So at the solution, we have this equality to be satisfied. So this type of problem is called a generalized eigendecomposition problem. Right? Okay, so the W then must be the generalized eigenvector of this pair of the SB-SW pair. Right, so generalized eigenvectors are defined for two symmetric matrices, pairs of symmetric matrices, and this quantity, the scalar quantity here, is called the generalized eigenvalue corresponding to W. Right, and that's what we were trying to maximize. Right, so W then must be the generalized eigenvector of this pair with the largest generalized eigenvector. Generalized eigenvalue, sorry. Okay, so you can think of it like this. Actually, in MATLAB, if you do eig, if you used eig in MATLAB, it actually solves generalized eigenvectors and eigenvalues. If you give it two arguments, it will give you generalized eigenvectors and eigenvalues for the matrix pair. If you give it a single matrix, basically it assumes the second one is identity. Right? So this one is identity. Right, so eigenvectors are a special case of generalized eigenvectors, basically. Right, so when the second matrix is identity, you get eigenvectors of the first one. Another way to think about this is multiply the right side with SW inverse and left side. Right, so I can also write this as SW inverse SB. W equals W transpose SB W transpose S that W, right? So this is an equivalent way of saying the same thing. W must be an eigenvector of this matrix, right? So W is the eigenvector of SW inverse SB with the largest eigenvalue. So you can also do that, yes.
What does a generalized eigenvector mean?
So generalized eigenvectors, okay. So if we have two symmetric matrices, so two symmetric matrices, then you can talk about the generalized eigenvalues and vectors of this matrix pair. I've also seen this pair called a matrix pencil. I have no idea where that name comes from. Probably it makes sense in some context. So generalized eigenvectors generalized eigenvector value pairs satisfy these equations. Right, so lambda V is a generalized eigenvalue vector pair of this pair of matrices AB. Okay, so when these are n by n symmetric matrices, there are n of those pairs. Right, so there are n of these pairs. If you stack them in, if you stack the eigenvectors, generalized eigenvectors, into columns of V, so you can write these as just stack them side by side. So you can do this. So in matrix form, this becomes okay. And again, remember, eigenvectors of A, eigenvalue decomposition of A, eigen decomposition of A is going to be a special case of this when B is identity. Right, so when you plug in B equals identity, then you have your usual eigenvectors of A and eigenvalues for those. Right? But you can generalize to a pair like this. Basically, you're generalizing from the second matrix being identity to something else. So these types of quadratic function ratio maximization situations arise frequently when people are dealing with these first and second order moments. And I mean, if you have a signal processing background, you could think of this as signal to noise ratio maximization. So I mean, this could be a filter that maximizes signal power over noise power that passes through the filter. Right, so if you're designing a signal detector in noise, this would be the optimal detector for some noise cases. Right, so everything, yeah. So if you have a signal processing background, everything we do in machine learning has a signal processing counterpart essentially. Okay, so these are generalized eigenvectors. Sometimes people call this matrix V, the generalized eigenvector matrix, the matrix that simultaneously diagonalizes the AB pair. So that's simultaneous diagonalization is seen like this. So so these eigenvectors are not orthogonal in general. In this case, so I need V inverse. That's not V transpose. So if you multiply from left with V inverse, basically, this will be a diagonal matrix. Let's call it diagonal A. This will be a diagonal matrix. Let's call it diagonal DB. Lambda is diagonal. So you have a diagonal matrix equals another diagonal matrix here. So that's why these generalized eigenvectors are also called vectors that simultaneously diagonalize A and B. Okay, so in this case, we're talking about these two matrices, SB and SW, right? So SB is this rank 1 matrix, how much the means are separated from each other, and SW is the sum of covariances from the two cases. Okay. So let's see how much time we have. We have 20 minutes. We can implement PCA or LDA. You'll do both anyway. So which one would you like to do right now? Let's see. Let's do PCA so I can ask you LDA. Okay. Okay. I'll try to use this computer. Is this on? Okay. Okay. It's too bright. Oops. Is there a way to? Is it too dark like this? I'm assuming these are. That might be your lights. No. How do I turn those on? Anyway, so let's sit in the dark. Okay, so. In case I recycled some code from G drive, let's keep it on. G drive, that wasn't G drive, something else. Looks like MATLAB is taking a while. Let's try this one. Looks like we don't have MATLAB. Okay, so I'll have to do something else. Hold on. I'm assuming this will not let me join Google Hangouts, right? Let's see if block the always allow. Maybe, okay. Oh, come on. So they really need to fix this. I'm gonna chase them. Hold on. Save, run, whatever. Yeah, sure, all of those. Yeah, of course I cannot install anything probably. Man. Okay. Looks like I cannot connect to. MATLAB was here. Okay, good. So I don't need this. I was gonna do a hangout with my computer, but okay. So let's do PCA. I'm assuming this will stay here. Okay. Okay, so let's do this. So I'm going to create a random sample from a Gaussian with 2 dimensions. Let's say 100 samples. So I'll pick my mean to be 0. My covariance.
Can you make the screen a little bigger?
Yeah, I can make the font larger. Yes, hold on. Where was the preferences? Maybe I should do this like. There should be a preferences somewhere here.
You can right click on the script.
Oh, right click. Oh, is it here?
Yeah, like page setup.
Page setup. Page setup. I don't see it. No. Okay. Is it this one? No. Well, my computer shows a preference button here. So
Dennis, can you post the code after?
yeah, I will post the codes after, but anyway, so I'll tell you what I'm writing. So small n for dimensionality of data, capital N for number of samples. So now we have 2 dimensions, 100 samples. So the mean of my Gaussian that I will draw samples from will be 0. I'll choose a random matrix A, rand n by n, and then I'll make a covariance out of it. So sigma is A transpose. Okay, so let's see. A times rand n and capital N plus mu. Okay, so basically what I'm doing is, let me turn on the lights. So if I take a random vector z that's n-dimensional from a Gaussian, that's 0 mean and identity covariance. Right, so these are normalized independent Gaussians. Then I can create a Gaussian X, Gaussian distributed X with this transformation. 5 minutes? Oh, it's not clear there? Sorry, the room is too dark. Oh, maybe I should turn on the other stuff. Okay, so I can take Z, multiply with the matrix A, then add mu, then this X will be Gaussian distributed with mean mu and covariance AA transpose. Okay, so and you can see that easily by looking at expected value of X is A times expected value of Z, which is 0, right? So it's A times 0 plus mu, which is mu, and covariance of X is covariance of AZ plus 0. So covariance of AZ is A covariance of ZA transpose, which is A identity A transpose, so it's AA transpose. So basically I implemented this here. I just picked a random A. So the covariance of the Gaussian will be random each time we run the code, but you can specify an A and stick to it. That's not the one. This is one. Okay, so it's really interesting. Now I have my samples X. Let's create a figure. And so I plot them. Okay, so these are my data samples. Let me make those. Let me make these actually separate plots so we see them side by side. So we'll find the principal components and plot them. Okay. So I have my data samples in the columns of X. I'll estimate its covariance. The true covariance is AA transpose, but I don't know that. So let's say I have a mean estimate. So let me just check to make sure I'm using mean correctly, because MATLAB always takes samples to be transposed compared to what I always like them to be. Mean value of the elements in X. Mean along the dimension. Okay, so mean along the second columns. Let's call this sigma hat. So that's my estimated covariance. Okay, so I have my estimated covariance, estimated mean. I'll subtract call it x0 mean, so x minus mu hat. This part is not that critical since we're generating x from 0 mean Gaussians. I'm basically subtracting 0 here. But okay, so y is, okay, let's do eigenvector. Let's use q. Sigma hat. Okay, so I'm going to take the eigendecomposition of my estimated covariance, sigma hat. So that's going to give me q and d, q for eigenvectors, d for eigenvalues. I'm pretty sure MATLAB sorts the eigenvalues, but just to be sure, let's sort them. So I'm going to sort the eigenvalues in descending order, and then I will shuffle the columns of Q to match this descending order of eigenvalues. Okay, so what we have here is, okay, so I generated data, two-dimensional 100 samples with a covariance AA transpose, mean mu, which is set to 0 right now. Estimate the mean from the samples, estimate the covariance from the samples, subtract the estimated mean from the data so that my data becomes exactly 0 mean, right? Then find the eigendecomposition of the estimated covariance, Q and D, sort the eigenvectors so that the first one is corresponding to the largest eigenvalue, then downwards with descending order of eigenvalues, and principal components are Q transpose X, right? So we have principal components in Y. If this sorting was done properly, they should be sorted from first to second, and then I should be able to plot the Y's here. So let's see if this works.
Is that V and Z that you plot?
X and Y. So this is figure 1, two subplots for X and Y scatter plots, and looks like it worked. So let's put this to the side. Okay, so our original Gaussian was tilted, right? And after we did PCA, the first axis, the first principal component has the larger variance. The second principal component has the smaller variance. Okay, and you see that the Gaussian got rotated to become aligned with the axes here, right? So this is basically PCA implements something like a rotation. It could also flip the sign. It could, right? So it implements a rotation, possibly combined with a sign change. So you'll take an ellipsoid that's tilted, and rotate it to become aligned with the main axis, essentially. Right? In the case of these Gaussians. Okay, so let's run a couple of times to see several instances with different covariances. You see that this time the covariance is a little more, the Gaussian at the top is a little more elongated, right? So this is, so since I'm generating these covariances randomly, sometimes the eigenvalue ratio becomes large, sometimes, in this case, eigenvalue ratio is smaller, closer to 1. When eigenvalue ratio is 1, you have a perfect circle. That's probably not going to happen here. Oh, okay, there. So, right. One thing that I want to point out is I used here axis equal after each plot, which forces MATLAB to scale these axes so that circles appear as circles. Orthogonal lines appear as orthogonal lines and not skewed. So I strongly suggest when you're doing visualizations of data in machine learning, make sure to use the equivalent of axis equal for whatever programming language you use, so that things don't get skewed visually and cause you to have some misinterpretation. Okay. So this will be on Google Drive. You can check it out and try with, well, unfortunately we cannot plot with more than 2 dimensions, but you can try 3-dimensional versions by switching from plot to plot 3. Okay. So let me see if I can put this to Google Drive. Here. Okay, so here. I'm assuming everybody has access to this shared folder, so you should be able to see this here. Okay. Any questions about PCA, LDA? I will definitely ask you to implement LDA, so make sure to ask about it.